Good morning, everyone. My name is Corentin Fivet. I'm professor at EPFL and the Smart Living Lab. It's a great pleasure to welcome Stefana Parascho today for this talk at the Smart Living Lab. There has been a batch of new professors. There is a batch of new professors arriving this year, and Stefana is probably the first one of that batch. For a long time, there hasn't been any new professor, so it's great to have young blood in the school. Maybe a bit about Stefana's past. So Stefana's got a master from the in integrative design from Stuttgart, which is one of the hotspots, worldwide hotspots for robotic fabrication in architecture. You got your master there. You worked a bit there as a teaching assistant as well, and research assistant as well, and then you moved to Zurich to do a PhD with Matthias Kohler and Fabio Gramazio, which is the other worldwide hotspot for robotic fabrication in architecture. So you did your PhD there and then moved to Princeton on the other side of the pond to work as an assistant professor for 3 years. And we are happy to have you here at PFL. And I don't say anything more because I guess that you will present more more yourself and in a better way than I do. Thank you very much.
Thanks, Corentin. I don't think I have a much better intro, but I'll still go through it again. Yeah, thanks everyone for joining. Thanks a lot for having me. It's nice to do my first presentation as somebody related to the EPFL. I think it's the first time I'm doing this, and it's nice to be in Fribourg. Yeah, I have a quick presentation, just repeating what Corentin said. I started studying architecture in my home country in Romania, actually, and after 2 years, I moved to Stuttgart to finish my studies there. I did my diploma there at the ICD-ITKE, and then I worked with computer engineering, with design production, and as a research assistant at the University of Stuttgart. So that's where I started working with robots and getting in touch with digital fabrication. I then moved to Zurich, where I did my PhD, where my focus narrowed a little bit more on multi-robotic processes. And then I moved to Princeton in February 2019, where I was an assistant professor for 3 years, continued work on multi-robotics construction and different approaches to it. Yeah, and then I came here, what is it, 2 months ago? March, April, May, 3 months ago. Started here the Lab for Creative Computation, also called CRCL. We used to be the Create Lab Princeton, so it's you see associations between the Create Lab and CRCL, that's me. It all builds up on the same work. So yeah, what are we actually working on at CRCL? We focus on how to develop and integrate new technologies, digital technologies, in particular robotics, into architectural design. And I'm particularly interested in the relationship between design and fabrication. So rather than just developing new material processes and implementing them, I like to explore where these processes make a change in the design process. So how can we as architects and designers really make use of them? Why robots? I think we're all familiar with robots, mostly from the manufacturing industry, such as big power plants, where robotics has been adopted mostly for the repeatability of tasks. So the same object is made hundreds and thousands of times, and so the implications in cost and time are minimal. We've seen similar intentions in construction ever since the 60s. Actually, this is the motor mason, one of the first one could consider robot. It's actually a manually guided machine, but it automatically places bricks. And these efforts have also mostly focused on automating simple standardized processes that can then be performed quicker and maybe cheaper, but that do not necessarily allow for customization or adaptation. So They're based on the same process that we know from manual labor, but automated into robotics. However, the potential that we see in digital technologies, such as in robotic fabrication, it lies exactly in dealing with individual constraints, with bespoke elements, and with differentiation. So a robot actually doesn't care if it does the same thing 1,000 times or if it does 1,000 different things. So there is clearly a potential in robotics beyond automating the same repetitive tasks, but towards more bespoke tasks. And rather than replacing humans, automating human work, rather focus on what can robots do better than humans, and what can humans still do themselves, and where does this connection between the two happen? We've seen a lot of projects in academia for, I always have to calculate, I don't know, 20 years now. Every time I do a presentation, it's more and more. So there's really been a movement in embracing this particular potential for differentiation, for new design possibilities through computational design and by fabricating complex geometries. So this goes from examples like bespoke walls that are made of standardized bricks, to spatial structures that require individual placement, and also to new material processes that are engendered through the use of robotics. At the same time, the industry is still pretty much concerned with the automation of standardized processes and the increase in productivity and saving. So that's where we're standing right now. And what all these projects have in common, and that they all target questions of how can we build new complex geometries, or how can we optimize construction based on material, time, cost, etc. What we're not asking that much is what do these digital technologies enable us to do as designers and engineers, that what can go beyond the complex geometry, and how can we access maybe unexpected goals, unexpected applications by harnessing the potential of these technologies. So in my work, I like to take a few steps back. I like to focus on our relationship with the machine. So where does the human belong in the loop, rather than where can we remove the human from it? And also question the hierarchical process of you first design an object, then plan it, and then execute it, but find new connections and new places for the machines in these processes. So I want to walk through a few projects and give you an idea of the sort of applications and the questions that I focus on in the work. And they all revolve around the connection between designer and machine by exploring the different ways in which materials, structure, fabrication, algorithm, and design can inform each other. So starting with the relationship between structure and fabrication, this is a project that was searching for ways of reciprocal information flow between design, structure, and robotics.
Prochain arrêt, Romont. Les voyageurs en direction de
How did we get onto a
pour
train?
prendre la correspondance.
Someone, okay. All right, I'm not in the train. Oh, okay. Oh, good. No problem at all. It was just funny. Going back to the brick labyrinth. So this is the first project I'll talk about. This is a teaching project. It was developed together with students of the MAS DFAB at ETH Zurich during 11 weeks. That was when I was doing my PhD there. I did some teaching. And the project focuses on brick construction, which is a very long established tradition in robotic assembly, and maybe the most known types of projects rely on robotic brick placing. But what was different about this project is that it only utilized dry stack bricks. So there was no glue, no mortar involved in the process. We wanted a reversible construction process. So the obvious research challenge was how do we combine structural stability with sequential fabrication to achieve a stable but and also reversible construction process. So how do we keep that thing standing up, actually? So instead of reverting to complex structural softwares, we actually chose to develop our own simple geometric stability analysis together with the students. That also gave the students a good way into programming and working on their own tools. And to make up for abstractions of both geometry and material properties, we validated the tool through physical tests. So you can kind of, I think here, yeah. So you can kind of see where it turns red, it collapses, yay, it all fits together. And the students went even further. So through these physical experiments, they discovered that if you have a double layered wall, you can get more stability through the friction between the bricks that are connecting the two wall layers. So in this case, it was supposed to collapse where the bricks turned red, but it actually kept turning up because of the friction between the bricks that keep those two walls together. So that way, the height and the leaning angle of the walls could be safely increased beyond what the geometric analysis would tell us that was possible. So the process of designing the labyrinth, it really required a constant feedback between the geometric analysis, between localized physical tests and the design itself. But at the same time, it allowed students to get an experiment-based understanding of the system that they were working with, which would not happen in a top-down approach, even with the best, most complex software. The complexity of the design problem, it increased with the fabrication, since we relied on a sequential assembly process where the walls had to be constructed in an order that ensured stability, reachability, and no collision between the robots. So we had to develop methods for both sequence generation and robotic control. And mainly because we used two robots that were both connected by a gantry, which could move in all directions. But we had to find a sequence where both robots could reach every target they had without getting into each other's way, and at the same time make sure that that sequence stays stable. So ultimately, the labyrinth was fabricated using different types of robots of different scales and sizes. So you've seen the small UR robots, they were used to prefabricate brick stacks that are then picked up and placed by the large robot arms in the RFL. And the reason we did that was to increase the speed of fabrication, because the long way of moving the gantry back and forth was the slowest movement. So by picking up, I think, 7 bricks at the same time, we managed to increase the time pretty dramatically. And at the end of the day, we managed to construct the labyrinth in less than 3 weeks, which was about 3 meters tall and had almost 10,000 bricks. Yes. Yeah, I'll start it to the end. That's the time of the students. We also disassembled it at the very end, not robotically. We did a test of the robotic disassembly, and surprisingly, it was very, very straightforward. We just had to reverse the code. But then it turned out that it was quicker to do it by hand, to be very honest. Speed is not really the focus of the research that we do there. It's more testing new processes. So, yeah, that brings me to the next project, which was focused on specifically on developing procedures for designing with highly complex constraints, such as those that result from multi-robotic processes. 1 second, I'll be right with you. So this is my PhD thesis, which focused on cooperative robotic assembly techniques for the construction of bespoke space frame-like structures. And by using robots cooperatively, it allowed me to build spatial structures without the use of any additional form or false work, eliminating the material waste during construction. So while the construction method is straightforward, we have 2 robots that alternate the placement of elements, so that one robot can constantly act as a support and the other one can bring a new element. The implications on geometry, material, and structure, and thus on design, they resulted in highly complex dependencies between the parameters, the different parameters that we're working on. And these are really not easy to address. So I'll give you an example. While looking for a new connection system that allowed for simple fabrication and geometric freedom, so without the use of prefabricated additional elements, we really wanted the connection to be quick and be implemented in the robotic process easily. I proposed an open node where only 2 bars connect one another in a point. So you avoid having to get all of these into one. However, what every engineer knows is that the shift in the bars, it leads to bending moments, and it reduces the stiffness of the entire structure, and it's basically really not what structurally efficient system. So to counteract this effect, I introduced a second connection point in each joint that results in close connections at every corner, so to say, at every node, and that dramatically increases the stiffness back. So it actually, we did some simulations, and it turned out that it's actually stiffer than the typical system. Now this is where it gets more complicated. Because it looks like the problem solved, but what the second connection point actually led to is that at every construction step, every single rod had to be tangent to two existing rods at 2 points. So what this basically means is that every single rod has a very specific position in space and orientation, which is only the result of the sequence and of what has already been built there. What it means simply is that the solution space for all possible locations of one bar that is connected to these two given bars, it needs to be computed so that all the perpendicular relations in a connection are fulfilled. And if we take two bars and we look at all possible positions of the third bar that is tangent to these two, and we add all sorts of different sides that we could add this bar, we can visualize the totality of the solutions. But more importantly, there are areas where there's no solution. So it turns into this relatively complex solution space, which is not intuitively graspable or imaginable. So what it leads to is that you end up with these nodes that are quite unthinkable to have been specifically controlled by a person where these bars come. However, they really have been computed and are only a result of the construction sequence. If you build the same thing in a different sequence, you actually get a different node, and you get different locations and orientations of the bars. You get a different behavior, so the whole thing really connects to one another. And these nodes where the bars come together, they define the whole local and global configuration of the structure, and with it, the structural behavior. So these are 3 examples with identical node locations, but with different connections between the nodes, as imagined if you had a different sequence. And the behavior is really, it's very, very different. It can't really be intuitively compared and connected. So what I'm saying is that we need computation to solve all of these connections, but we also need new ways of understanding what's going on in these systems through good visualizations and analysis that can help the designer understand what they're working on. For the materialization process of the structures, I worked with a material connection that was both easy to execute and very strong with welding and steel rods. The welding process is implemented manually, while the robots are used only for positioning and for holding the bars in place. And this is mainly because humans are a lot better at doing intricate movements and reacting to, say, if the bars aren't perfectly aligned and doing these sort of movements of the welding system, whereas robots are really good at holding elements in place precisely, spatially, and they can keep them up there for as long as we want them. So combining the two strengths was really one focus of the project. It's a typical example of where it makes sense to separate these tasks rather than go for full automation and just want to have everything done by the robots. However, the main challenge in terms of fabrication was the robotic movement planning in a setup with multiple machines that are working in the same space with a structure that's continuously changing. The possibility of collisions is really, really high. So it's again a system that's not intuitively solvable. A person doesn't really intuitively understand how the robot moves. You can control how the end of the robot, the gripper, basically moves through space, but the way that the joints are calculated to make this movement is really not predictable. So this really required specific algorithms that exist in robotics to be used for path planning so that you can get these moves without them getting in each other's way. Our task was really to get them connected to the environments that we work in as designers, the 3D modeling environment, and to have easy access to them. So all of this led to a sequential design process that utilizes structural optimization and fabrication information as design drivers, rather than as in conventional processes in a post-processing step. However, I did break up this process into 4 separate steps to maintain a better overview of the process and to simplify the problem, as all those relationships became a bit complicated to deal with. And yeah, all of it finally enabled the design and construction of large-scale spatial structures, such as this one. This was the largest that I tested, which consisted of over 300 elements. I think it was 300 connections, but I don't want to say. I'll have to probably more. What I want to say with the project is that using robotics in construction for really bespoke and complex geometries, it can quickly turn into a rabbit hole of dependencies and unintuitive problems that as designers, we're not always fully prepared for. And while it was, I was able to solve these things through computation, simulations, all the tools that we have, I think there's still a long way to making these technologies more accessible for designers and really easily usable in the design process. So rather than having, black box tools where you just press a button and you get a result, I think we need better tools for visualizing, communicating, and understanding these design spaces that open up. Okay, so that brings me to my next project, which builds up actually on the previous 2 projects. It combines cooperative robotics with structural form finding to further decrease both material in the structure and material waste for the construction of vaulted structures. So the Light Vault, it's a collaboration with SOM Engineering and the Form Finding Lab at Princeton. It's a project I did during my time at Princeton, and it resulted in a prototype that was exhibited in London. Unfortunately, only for a very few days before the pandemic kicked in. We really just managed to finish the construction and then had to shut it down. The project focused on finding new ways of constructing vaulting structures out of heavy brick material. And it uses the same principle as in the spatial structures projects, where one robot acts as a support and the other one brings an element, and that way we completely eliminate the need for any form or false work. So the challenge here was figuring out a design that worked both structurally and for fabrication constraints. The result is a glass brick vault that's constructed with 2 robots, starting with a cooperative assembly of the middle arch. So you have 2 robots putting this arch together and then it continues with the robots working individually from the arch outwards to complete the structure. The figuring out the design space for the vault itself, it really required looking into the robotic constraints and parameters. So the geometry is, on the one hand side, it makes sense structurally, and we were able to give these constraints to the engineers, and they generated a form through form finding methods. So this double curvature that we got in there was actually useful, but it is a direct result of the movement space of the robot. So where they can reach to do this middle arch cooperatively, and then how it moves up because they need to work basically above their own heads. This really defined the design space. There are strong temporal dependencies. So we had to define a pattern and a sequence that made sure that A, it's stable during construction, and B, that the robots can reach it. So I like to show this slide because the sequence on the left side and on the right side is actually different. And that's because of the herringbone pattern that we used to do there, but also because we chose the sequence such that every brick always has 2 sides of the existing structure that it can lean to. So it's never just floating so it always has two connection points, which helps maintain stability during construction. We did use glue, because that's something I sometimes forget to say. That's a bit confusing. We did use glue between the bricks. On the one hand side to fill the gaps, because the bricks have their standardized shape, and through the curvature you have gaps that develop. And on the other side, because we had to ensure stability during the construction, and also we built this thing with the exhibition open, so there were people everywhere. Didn't want anybody to get a brick on their head. So I have one video that I'd like to just run. Just for the vault. Where we actually final structure gallery of the Western where we had the robot that hard to get. Yeah, that was the final result. The vault did turn out a little bit smaller than we initially planned, because as we were building it, we were dealing with lockdown changes, situations, and at some point we had to like decide, okay, we have to start properly. But we're very happy that we got it. So, okay, I have a few more projects. I'll make sure to stay on time. But currently, some projects that are more recent, we're dealing with the question of how we can make use of material beyond the shortened time span of construction. So can we use robotics actually to reuse material rather than to build new geometries, new complex shapes from new material? This is Zero Waste. It's a collaboration with Professor Erin Dessler from Princeton University, in which we investigate what role robots can play in monitoring and engendering material reuse. So the project wrote a question about impact and time. How can we address sustainability beyond just optimizing for the amount of material that is used in construction? So we looked at the life cycle of materials and how much is wasted in construction, and we identified two questions. How can we work with existing material that's currently in use in buildings? And can we reuse it for new constructions, but also how can we plan and build new buildings such that they facilitate the reuse of material in the future? That's the long-term plan of this project. We went all in. This is Erin and me. We handpicked a number of wood elements from the local recycling facility in Philly, which we then assembled into a shed by hand this time, it's supposed to be representative for the typical American wood frame construction. And then what we're working on now as well is investigating how we can use the robots for the disassembly and for reconfiguration of such structures, which also involves how we can develop scanning and tracking system that not only recognizes the material component, but it also visualizes this type of information for non-expert users to increase awareness for reusability and for materials. So currently, I think this happened last week, to finish the first step of disassembling a part of the structure. What we are planning to do is to then reassemble, so reuse those elements to put back together to make a new design, basically. And while robots are really the main part of my work, I think it's also important to focus on the relationship between humans and algorithms, maybe not just involving robots, and also where can we have an impact on the experience of humans, on the spatial experience. So this is a project, Total Signals, that I did at Princeton University as well. It focused on how we can use new technology to improve our spatial experiences, particularly during the pandemic. So it's based on images that we all know and have seen, where social distancing was really at the base of our experience, and spaces were plastered with signs and markers and stickers, static rules. And the project, it aimed to address the need of regulating the distance between pedestrians, specifically in indoor spaces, by proposing an interactive system, which was using real-time light projections and an algorithmic prediction system about human movement behavior. So by tracking pedestrian movements and then suggesting routes and safe areas, we were aiming to free up public spaces from the rigid rules of social distancing, while being able to adapt the visualizations and the rules to based on how things progress, based on how the spaces were used. So just proposing a very adaptable system. By using well-known people detection and tracking methods, this is just an example, it's not even what we use. But we integrated these into a smart projector, which uses a projector, a mini computer, and a camera, and then ultimately it projects indications of safe trajectories on the floor. The system is dynamic and adaptable, so it can be combined into a bigger system with multiple projectors, and can react to the given spatial configuration. What's important to know is that we did make privacy a primary concern. We worked only with geometric localization data, so any image, video information was translated into a point and a trajectory in space. And that was only computed on the mini computer, not even downloaded to our own laptops and then deleted. So there's no identifiable information that was processed. These are very initial of Eric, who actually developed the project working on a detection and tracking system with the projector. We then used a deep learning-based approach for pedestrian detection, as this allowed the projector and camera to be used in as many different types of spaces as possible. We still have to make our own model and gather the whole data, because there aren't surprisingly many models of people from that perspective in indoor spaces mostly. There are from drones, but a lot further away. So we then worked through a few visualizations, and while we started designing the visualization around COVID and distancing and how we can make sure people understand where to not walk, we quickly realized that also with the progression of the pandemic, the public space gained a much larger importance than keeping people away from each other. So we actually we moved from focusing on how to distance people efficiently to a visualization system that could help bring people together and connect them. The visualization itself is done with shaders and open frameworks such that the colors reflect the interactions between people. And by playing with the hardness of the borders, when you face towards each other or away from people, we were able to customize the visualizations so that they can really reflect how people interact with each other. And I do have a few visualizations. I don't want to spend too much time on them because I know I'm maybe I'll find one where there's something happened. There we go. But we installed it in Princeton at the School of Architecture over this landing of the staircase so that people could really use it. And what we did observe is that people did use it a lot, and it did encourage people to stop and play with it and really test out its limits, which is really nice. And we're planning to actually set it up at EPFL at some point. The fall, maybe, hopefully, latest in the spring, but also to expand it, we want to continue working on the visualization and how we can really customize space and work with dynamic visualizations for better. It was fun. That's a good thing. So yeah, this is where we're now. We're focusing right now a lot on questions around the role of humans in the process. So especially how we can go beyond optimizing existing processes and solving problems, but to explore creativity as well and the impact that robotic technologies can have in the creative process. Some questions like how can humans and robots co-design and co-fabricate structures, and what would be the benefits of such processes, the parameters, the constraints? What can we get from machines beyond the cheaper, faster process, but maybe towards a more creative one that can lead to new, unexpected solutions to the problems that we're facing right now. And to sum up, I think it's important to break down the hierarchical design processes that we're used to, which are based on a single directional process. You design, you plan, you build, but find ways to integrate them. Different components, like questioning how we make the decisions in the design processes, how does information flow from machine to fabrication to design, and what the role of humans is in these processes. And I'll just stop it here and credit a lot of collaborators and students, architects, engineers, biologists, computer scientists, etc. that we work with, because none of this would work at all otherwise. And yeah, well, thank you. Robotic. Should I just turn it off? Sure, sure.
All right. Thank you very much, Stefana. That was very inspiring. A lot of new things that I didn't know, so it's nice. Thank you very much. Is there any question or comments also from the Zoom? Already one? Yes, I don't even need to ask my backup question. Perfect. Please.
Thank you for your presentation. And I was wondering, do you think if there's flying robots can play a role in the fabrication process?
I think drones.
Yeah,
there's been some research on that. I think Robotics had a few projects on it.
And I do think there's space for it. The main problem with drones is that their payload, basically, they need to be light to fly. And then with construction material, that limits it a lot. So the projects that I know, they mostly work with tensile structures, really light, things like that. So it's a limitation. And then also the precision of flight, which I'm sure is getting better and better and better. So that can probably be overcome. But the payload is really a tricky thing for construction. But there's roles of like scanning, monitoring, seeing things that we don't see. I think they can be very useful.
It's a similar question about robots on wheels.
Yeah.
What are the limitations?
The limitations are really difficult to control or to get to work. I mean, the reason we want robots on wheels is because we want to put them on construction sites. The construction sites are really messy and uncontrolled, and localization is a big problem, precise localization, but also making sure it's just, I don't know, tipping over and then it's stuck there and it weighs 2 tons. So there's a lot of research going into that. But I think it's one of the biggest challenges we have to get to.
Yeah, maybe that brings me to the question whether these types of robots have been used on real outdoor construction sites yet.
Industrial robots? Or general, yeah.
The ones you've been studying.
Yeah, there are applications. I'd say there's more development in the whole 3D printing part, where you don't even need the whole robot with all the 6 axes, but it's more of a 3-axis thing. There real project, there's been large-scale research projects that they've been used, right? The DFAB house, that they've really brought them on site and done stuff with it. In industry, they're mostly used in prefabrication, because then you have a lab environment and you can really do everything there. In wood construction, they're used quite a lot nowadays, in Switzerland at least. On sites, you end up with the problems of localization and precision, etc. So there's less use seen there.
Like for the deconstruction example you showed, could we imagine having those rails placed outdoor beside the structure that needs to be deconstructed, and then the robots being placed there for I don't know how long they need to deconstruct the structure?
Yeah. I think that's.
Then they wouldn't have so much of localization problem, no? If they're
fixed on the ground, you localize them once and then they're okay. The main issue there is scale. That's something that always comes up. They only have a limited reach, especially if they're set on the ground. So that's why we think of mobile machines, because then you can cover a lot larger areas. But for the limited range, I think could totally be used.
And can I
yeah.
What are the largest ones that exist then?
I don't know exactly the number for the large. I'd say 3.5 to 4 meters, maybe. We're getting some that are 3 meters reach, so I'm really happy with that, but I'm sure there's bigger ones. Yeah.
Is there a question from Zoom?
Not yet.
Yes.
I would have a question. You talked a lot about the relationship from the designer to the robot, but for me as a non-specialist, I don't know a lot about the robot design. It looks, to say it a little bit in a provocative way, it looks as less intuitive to use the design tool you propose than the usual design space I have as an architect. So I wonder how do you bring this to normal designers as me, who cannot program or not familiar with this, and what is how much these design tools will be democratic or can be used by everyone? Because what you see a lot is that you have them very specialized spin-offs, and some people can use these tools and for very specific designs, but it's not spread out widely. So how do you deal with this?
Yeah, I think you're right. They are a lot less intuitive to use than traditional design tools. That's really one of the challenges to work on. And I think what's happened a lot is developing more and more complex tools to deal with the complex parameters, such as, say, path planning, where you have to come up with the solution how the robots get from one point to another, or sequencing, etc. So a lot of effort has gone into making these tools work in the first place. I think what's really missing, and I don't have it here, is good visualization tools that can really show a designer what the design space is that we're working in. Because the moment you put a robot, you have, it's not just the reach, say it can reach 3 meters, which means it can reach everywhere. It depends on the tool that's on there, it depends on the orientation that it has to go, it depends on what's been built up, right, that there are no collisions. And I think there's geometric ways of really visualizing that and working with, if I place a brick here, I'm blocking my space to go somewhere else, right? Or can I reach in the back? Will I not be able to reach? And making that more accessible to designers, I think, is something really, really needed. And on the other hand, it's also a process that it's not intuitive at all. It becomes intuitive if you work with it. So everybody who has worked with robots, at some point you kind of know where can it go, what can I do with it, but you cannot expect architects to, you can't expect to tell them, well, go for half a year and play with the robot so that you can use it. So I think it's really getting that intuition through the modeling tools that's necessary. In terms of having the tools available, the movement is towards at least having open source tools. Everything is accessible, or not everything, but the tools we work with really are, so that other people can also contribute to them, etc. There's still, you do need specialized knowledge, right, to develop them and to really get into it, but I think everybody's working towards making them more intuitive. It's maybe a bit of a longer path than we would have liked. But that is the goal.
Maybe I have a question somehow related to that.
Yeah.
So in your PhD work, so you explained well how all the constraints and the design space for local assemblies, but how was the large assembly controlled? How did the designer fit the overall shape that you are targeting, or was it target shape? Was it something else?
Yeah, I did specifically. I have it here. I broke it up into a few steps. So my ideal scenario would have been I develop a tool where everything comes together and considers fabrication and considers structural constraints, and it considers everything, and it allows you to design what you want. Yeah. Of course, it didn't happen because it's complicated. I did break it up into 4 individual steps, and the way I designed was with the nodes. So you could start with a target shape, so to say, where you could place nodes around in space. That distribution was kind of up to you, but it was also just an initial distribution. So you have the nodes in a first step. The tool would then generate a topology, so figure out what could be a more efficient connections between them with the 3, because you need 3 bars at a time, and the sequence that's needed. And in a second step, there was structural optimization where the points actually got moved around to minimize stresses. So, and then in the next step, there was fabrication data and path planning generated. If something didn't go up there, you had to go back. Ideally, you have that integrated too, and you don't have to have 4 points, or if you have a problem with the 4th point, you have to go back. That's still.
So you ended up with a tower or sphere because
that's how
the set of points.
Which then still were allowed to move around, but that was kind of the design intention.
But when that's also the designers may not need to know anything else than this.
Technically, yes.
Is it how you see it, or is it
not really?
Does the designer have to know how it's made, or do you see it as more like a ready-to-use plugin, and then you say, oh, I want a sphere with that type of assembly, then okay, here is the plugin.
I don't think that works or will work at any point, and I think it also brings too much distance between the designer and the actual process to have like a press a button, here's your thing, and also I don't want to say it's just a psychological thing. I think it's a valid point that you might get a result you don't like. So you want to have control in there at some point. I think what's needed is to make the possibilities easier to understand. So to actually get designers the understanding of the processes, but in a quicker, easier way, other than putting them in a room with a robot for 6 months, which should be through these tools. But I'm not a fan of the ready-made plug-in button, here's your, also because you only get one type of structure. I think tools that allow for different processes, for different materials, different systems, where the designer can actually interact and react with, I think they're a lot more useful. And also in the fabrication process, I think what we need is less predefine everything and then let it run, but have ways of interfering in the process, of interacting, of telling it, I know, this doesn't seem to be working as I thought, so stop and try this, like really easy interaction between humans and robots.
But I think this is an interesting point because, yeah, as an architect, you're interested in both on the general design, but also on the local design. But here, the local design is mostly computed, and it gives you some interesting tectonic, which is very appealing for me. But then I would not, I don't think that as an architect I could be able to control all these tectonic points. So I would be more interested in having a general tool where I could draw some, let's say, general design space which I would like to have, and then to see what, with the help of computation, what alternatives I could have, or how could I modify this? What happens if I a little bit like a nerves curve or something like this, where I can have some angles and to think, okay, when I try to modify the shape, the local solutions get different. And so it becomes again, let's say, intuitive, because you can learn it by manipulating
that's somewhat of part of this work, not all of it, but you could, move the nodes around and then see how it changed. I think there's a bit of an issue in working with different options, or at least when the design space is so large, there are just so many options that then there's a question of how do you navigate that solution space. There's, I think, a ton of, or not a ton, there's a bit of research in that direction too. How do you help visualize that solution space and guide them so that it's not just here you have 1,000 options, pick something. But yeah, I think many questions.
I would like to take the discussion to a different path or branch and ask what is the real benefit of using robotics for construction at a later stage to be used and overall for a more sustainable society.
Okay. All right.
Because let me add something on that. The use of robotics for assembly and construction, fabrication, I understand it has a lot of benefits because of the precision that it offers.
Yeah.
On the other hand, when we want to deconstruct things, do we need precision? And this is maybe a vague question. Or do we need so elegant moves that robotics offer, or is it maybe more sustainable eventually to do it manually with less precision, but on the other hand, with less constraints as well.
No, I think robots for disassembly reuse cases, their role is in assisting and really adding, so what can robots do better than humans? And one is precision, and I think you can really make use of precision in disassembly processes too. If you have many elements, even just computing a sequence that everything stays stable, and then you have the robots easily go, you don't have to figure out where's what, can I do this, can I do that, I need to support it here, where do I move? But if you can compute all of that and have them just do it. But I think the assistive part is really important, because you work with big elements, heavy elements, people can do it, but I think there's a big gain in having robots that can support things for a long time. You could even just have it hold an element which is structurally super important and just take out a lot of other ones without the need of additional support structure. You can minimize the use of extra things that you would need normally in a manual process, and also the logistics of it. That's right.
And also the life of a human is so far more value than the one of a robot.
Yeah. Yeah.
So if it falls.
Yeah.
But then if it's about supporting things, then you also have constraints because of payload. So
yeah, but the robot's payload is going to be higher than a human payload, or it can be higher than a human payload.
But in that case, it's a big discussion.
No, but that's why I'm here. I don't think it's all solved and, you just put robots on site and they'll take anything apart, but I think it's the same questions as for assembly for me. It's robots can do certain things better than humans, so that's where you want to employ them. And that's precision. And for this assembly, it's less about place it in the exact orientation, but it is about pick out the right one and move it out, maybe the extraction path, like there. Precision and then support. I do have another one, but that's also in reconfiguration processes, for example. Like if you have if you want to take something and reuse it, if you want to reconfigure a structure and not just take it all apart and put it back together, what you would traditionally do is take everything apart and place it, maybe, I don't know, figure out what elements you have, what you can work with, and put it back. And if you can make use of computation and have the robot's precision, you basically pick it out, figure out where it goes, place, do the disassembly, reassembly in one process, which saves a lot of logistical effort. Johannes is not convinced. Well, talk about it.
We have time with that.
That's good.
Yeah, last question is in this interaction between a robot and a human, if there's some kind of sensing abilities, for you, which one would take over the other one? Would human feedback or intuition have more value over sensing abilities, or if there would be a conflict at some point?
You mean if
I don't know, it's
it's like
one has more value.
self-driving car,
Yeah,
well, I don't know if I have the answer to that, but that's, again, with all capabilities of robots, like sensing capabilities are also very different between humans and robots. And I think ideally you want to use both.
Mm-hmm.
So humans are good at intuitively dealing with complex scenarios. They're just like, I think we're going to try this without necessarily knowing exactly why and analyzing it all, whereas computers and machines are really good at analyzing a lot of data or complex data. So I can imagine scenarios where you'd rather have a human just say, let's try this, rather than run the 50,000 simulations of that. But also other scenarios where it's very easy to recognize something for a machine, whether it's through vision or force sensing or distance. I don't know if it would ever get into a complex scenario, because I wouldn't know why.
Yeah.
All right. Thank you. Thank you. Thank you, Stefana, for the talk. Thank you, Laure and the Smart Living Lab for the organization. Thank you, everyone here, for the nice discussion. I think we can only conclude and hope to reach past. Thank you for joining.
Thank you. Thanks for having me.